Welcome. So the topic we'll be discussing in this lecture is hardwired control. Okay. So you may ask what is meant by hardwired control. So last class we have discussed uh, how a sequence of instruction is divided into several subtasks and how it is being carried out by a processor. Okay. Uh, but in this lecture we are going to discuss more in detail, like physically in reality how the processor is going to generate the appropriate signals so that certain task will be performed, right? Okay. So so for executing an instruction, the processor should generate the appropriate control signals. Okay. And these control signals should be generated in the proper sequence depending on the type of instruction getting executed or in what order the programmer has written the instruction. So based on that, these control signals should be generated by the processor in a proper sequence. Now, how to generate this control sequence? So generally there are two ways to generate the control signals. One is by using hardwired control and the other one is by using programmed control. Okay. Hardwired control means for every instruction, a hardware connection will be created temporarily. So that is what is called as hardwired control. Okay. So whatever the instruction, whatever a typical instruction, accordingly the hardware lines will be enabled. Okay. It is something like there is a one hardware unit is connected to another hardware unit. Okay. This is hardware unit 1. This is hardware unit 2. Okay. There may be many lines between these two hardware units, maybe some 10-20 lines will be there. Okay. So currently what operation you are doing, accordingly any one of the line will be enabled, right? Maybe one line maybe to perform add operation, then that line alone will be enabled. I'm saying one broad example. Okay. And another line may be to stop the execution, so in that case that line should be enabled. Okay. So the thing is, whatever you want to perform, everything will be controlled uh, through uh, through through hardwired program. Okay. So that is called as hardwired control, right? There is no programming here. Everything will be done through physical signals through the hardware. So that is called as hardwired control. And the second way of generating the signal is by using microprogrammed control. So this is a type of programming. For every instructions you will create a set of micro instructions, and this based on these micro instructions the processor will perform the task. Okay. So these are the two categories by which the processor can generate the control signals to perform a particular task, right? So in this lecture we will be focusing on hardwired control, where the control signal will be generated by hardware connections. Okay. Fine. So is there any advantage of hardwired control or microprogram control? Yes, its own advantage. So the advantage of hardwired control is it will be very fast. It will be very fast because they are because it is directly the hardware signals, the hardware units were connected, and the signal is created from one unit. Signal is sent from one unit to another unit, so it will perform very fastly. Okay. But the disadvantage is it does not have flexibility. You cannot include all kinds of flexibility in hardware control. Okay. The flexibility is limited because when you connect two units with some certain wires, then what does it mean? Certain lines, then what does it mean? It can perform these two devices can be uh, can can communicate only to send only these signals. It cannot send some other different signals. Okay. So the flexibility is limited in case of hardware control, but with respect to speed it will be very fast. Okay. Whereas the microprogram control is other way around. Its speed may not be that high, but it is more flexible because according to the requirement, the programmer can change, can write the programs, right? Fine. So today's focus will be on hardware control unit. So how this hardware control unit is organized. So that's what we are going to discuss. So this is how you can visualize the hardware control unit. There is a clock which controls counter. Okay. So depending on the clock steps, the counter will create appropriate steps. Step 1, step 2, step 3. Okay. In step 1, some set of instructions will be executed. In step 2, some other set of instructions will be executed. It is like that. Okay. So each step corresponds to one clock cycle. So if you go back to the previous thing, so for example, if you take this, here there are four steps: step 1, step 2, step 3, and step 4. So step 1 corresponds to one clock cycle. In one clock cycle, all these instructions will be executed. Are you getting? So whenever an instruction is executed, what happens? That instruction should be loaded from memory to what do you call? It should be loaded from memory to processor. Okay, but this is actually a this is actually what this is actually a sub task. This is actually a sub task. Your actual instruction is this. Your actual instruction is this. So this instruction will be first moved to IR. Okay, from memory it will go to MAR, will give a request, and it will go to MDR. From MDR it will go to IR, instruction register. Okay, now instruction register decodes this and it understands that R4 and R5 should be added and the result should be stored in R6. Okay, now how it is going to do? For that it is using these four steps. In step 1 it is going to do all these things. Okay, so here the step 1 is that, right? Step 1 in the sense, in first clock cycle, what are the things to be done? Okay, that instruction will be passed by IR. These are the things should be done, that will be given to the decoder or encoder logic, and accordingly those steps will be performed. Okay, and 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 external inputs, in the sense, these can be either interrupts which are created by some external devices. Okay, it includes interrupts, and also it includes MFC. In the last class we have discussed MFC, memory function uh, control, right? Complete memory function complete, whether memory function is completed or not. WMFC, wait for memory function to complete. So when memory function completed, that also will give a signal to the decoder or encoder logic. Okay. Condition codes represents all the flags. In one of the previous lecture we have discussed different types of flags, like overflow flag will set whenever there is a overflow when you perform multiplication, right? And carry flag will set whenever there is a carry. Negative flag will set when you add or subtract two numbers. When you subtract two numbers, the result is negative, then the negative flag will set. Okay. So this condition code represents those flags. Sometimes this flag values also may go as an input, right? and and depending on whatever the instruction that is getting, so IR can give different instructions to the decoder. Okay, so whichever the instruction so it has many lines, you can see it has many lines, so each line will represent one instruction. This may represent one instruction, this may represent some other instruction. Okay, because it's a hardware control, so like that there may be n instructions, each of these will represent one instruction. Okay, so if it want to perform instruction K, then it will enable only that line. Remaining all lines will be disabled. Okay, and the decoder will then decode and it will understand and it will perform that. Okay, right? So in a typical microprogramming or microprocessor, if you see, there are how many, the number of instructions are limited, right? Like add, multiply, divide, you can count. So for all the possibilities, the instructions will be available here. Right? So this is how it is working. Fine. Okay, so accordingly, any one of the instruction will be enabled, and whatever the instruction enabled, that will be decoded and it will be executed. Okay. So the in a typical microprocessor, if you see, the number of instruction will be limited. So for all the possible instructions, there will be different lines. Okay. But still you cannot say it is fully flexible. So that we discussed that one of the disadvantage of hardware control is it is not highly flexible. Okay, but its speed will be quite high. Okay, so this is the detailed version of this diagram, this control unit organization. Again, it is shown here in a detailed version. Okay, the encoder and decoder were separated out. Here you can see there is a decoder and encoder. Okay, but here both the things were separated. Okay, So there is a clock and the control step counter which creates a step decoder step by step. T1 represents what are the things should be done at time 1, that is one first clock cycle. Okay, then accordingly in that clock cycle what should be done, uh, that particular thing will be enabled by the IR. Okay, instruction decoder will decode those instructions alone, and it will enable the appropriate signals. Okay, it will enable the appropriate signal. So you can see here there are different signal, instruction 1, instruction 2, up to instruction M. So whichever the whatever the instruction that matches with any one of these instruction, only that line will be enabled. Okay, and then the encoder will perform that particular task. Okay, encoder will perform the particular task, and and that is how the things work. Okay, and here uh, you can see there is something called as run. So run is used to increment the step counter, right? So initially the step counter will be 1. Finally one instruction got executed, one complete instruction got, I mean one step 1, whatever the task to be done, that is done. Then the run will be enabled. Once the run is enabled, the counter will increment. Now it moves on to time 2. So in time 2, it will work on some other set of commands. Okay, so that command will be decoded, and appropriately some other instruction will be enabled, and that will be executed, so on and so forth. It goes up to time n. So for a given program, once all the time clock cycles were completed, at last the end signal will be enabled. Okay, so end signal will reset the counter to 0, because now this program is completed. Now some other program may execute. Okay, right? If there is any memory or memory operation is going on, say for example you want to read something from the memory, at that time this run will be temporarily disabled. Okay, when after executing every instruction, run will be enabled, so that this counter will increment. Okay, but when there is a read operation, and if the CPU has to wait for the read to complete, then the run will be made 0, so that the counter will not increment, but it will wait until the read completes. Once the read operation completed, again the counter will become 1. Okay, so these are so this is how the things are controlled, because we have discussed previously, if you remember, until the read operation is not completed, the processor has to wait. Certain things the processor can do, for example it can fetch the next instruction, but it cannot keep on doing, right? If it wants to, for example, we discussed one instruction something like this: add r1 comma r2. Okay, as long as that r1 is a indirect memory addressing, as long as r1 is not available, it cannot perform the add operation. Okay, during it may initially request to perform the read on r1. R1 represents some memory location, so the processor may move that address to MA, or and it will generate a read signal. Meanwhile it may update the PC, but after beyond that it cannot do something else, because after that it has to perform add can be completed only if the first operand data, whatever available in this memory is available in the processor. Okay, so in that case it has to wait. So we have discussed an instruction called WMFC, wait for memory function complete. So whenever this wait for memory function complete comes, then the processor has to wait. Literally it has to wait, it cannot do anything else. So 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 in that case this run will be made as 0. So when the run is made as 0, what happens in the sense, the control step counter will not increment. So it is something like the processor got freezed. Okay, it is not proceeding. So once again the read is successfully completed, then it will be enabled, so that the control step counter will increment, and the set of tasks in the next clock cycle can be executed. Okay, fine. So let us see how actually this hardware control works with some examples. So here is an diagram. What it shows in the sense, at this is the input to Z in. Okay, so this is the output of this circuit goes as an input to Z in. Okay, that is the Z register. Previously we have discussed the single bus architecture, no, if you recall. So in single bus architecture there is Z. Okay, so the input to the Z, okay, is given. Of course it is output from ALU, but in ALU there are different units, right? There are different blocks. Okay, so one such option is shown here for Z in. Okay. Okay. So what is there? Basically, there is a OR gate. This is a OR gate. So there is a OR gate, and this OR gate takes, it can take input either from T1 this unit, or from this unit, or from this unit. Okay. So whenever T1 is executed, that is whenever you are in time 1, okay, that is in the first time slot, Zin will be always enabled. Okay, how, why we are doing like this? In the sense, you may think it's not making any sense, but if you see the previous instructions which we have discussed, or add R3 comma R1, if you see this is PC out, that is whatever is in PC that goes to MA, or in MA or memory address register, then we give the read. Okay, then we select 4, that is the constant 4 is selected for the multiplexer. Then we add, what is added? Whatever is in the internal bus. At that time in the internal bus will be the output of PC. Okay, that is whatever is in PC. So previously, if PC contains 2004, that will be in the internal bus, and that will be available through B, and multiplexer has 4. So it will add what, 2000 plus 4, which is 2004, that will get into that will go to Zin. So here if you see, every time the first instruction is to read the current, I mean to move the, to fetch the instruction that is pointed by PC out, and to increment the PC. Are you getting? To fetch the instruction that is pointed by program counter. The fetch is not completed at this point. We gave a command fetch, right? And then we are incrementing the what you call, we are incrementing the PC, and that incremented value is getting into Zin. Okay, the old PC is incremented and that value is getting to Zin. PC also not yet updated. Okay, so here also this is happening. If you see the next instruction for branch, also the same thing is happening. The first instruction is same. Okay, this much is to give a command to fetch the next instruction pointed by the program counter, and this is to update the current PC, that is add 4 to PC, and that added PC plus 4 will go to Z register. Okay, so next, here also if you see in multi-bus configuration also it is same. PC or we are moving the, I mean whatever is in PC, that is moved to memory address register, and a read command is given, and we are incrementing PC. Okay, right? So so okay, so everywhere, or you leave the last case. In the last case, PC got incremented automatically. If you see this two case, in the first statement, always some input is getting into Zin. Always some input is going to Zin. Okay, that is in which step? In step 1. Okay, so that here we are saying that if it is step 1, okay, this is for single bus organization only, not for multi-bus organization. So leave the third case. So if it is step 1, that is time slot 1, Z will be automatically enabled. Okay, so whatever is in, then Z will be automatically enabled. Okay, Zin will be automatically enabled. That is because in time 1 we are going to use Zin. Okay, and in time 4 Zin will be enabled if it is a branch command. Again, why it is so? You see the branch code which we have discussed previously. Okay, this is for branch. So here we are using offset field of IR out. The offset field is added. Okay, the offset field is added with the whatever is in the updated program counter. Okay, and that output goes to Zin. Okay, so that the second, in the second case we are saying that if the fourth command, if the fourth command is a add command, then Zin should be enabled. Okay, so that is what the second command says. Okay, at time 4, if it is a, yeah, it is this one. Okay, not the, sorry, it is this one. At time 4, if at, at time 4, what is that? This is actually a, this offset, why we are using for branch instruction. Okay, so it is not connected with add, it is connected with branch. Okay, at time 4, if there is a branch instruction, then Z in should be enabled, right? So that here we got this. At time 4, if there is a branch instruction, then Z in will be enabled. That is, the 1 will be generated here. So even this is OR gate, right? So even if 1 is 1, so whatever the output, that will go to Z in. Okay. Similarly here at time 1, it will be always enabled. So whatever here, it will go into Z in. Okay. At time 6, at time 6, now that is for again for this particular instruction, if you see at time 6, what we are doing, whatever is in the MDR contains the first operand, that is R3. Okay, that is moved to the system bus. Okay, if that data is 15, that is moved to the system bus, and select y contains the first operand. If it is 20, then both will be added and the result will go to Z in. Okay, so in that case 20 plus 15, that is 35, will go to Z in. So that we are giving this at time 6, if the instruction is an add instruction, then Z in will be enabled. Okay, so that's what it says. So that is what this logic says. Okay, so it means that at T1, during T1, Z in will be always enabled. So whatever the output generated at T1, that will directly go to Z in. Okay. At time 4, if it is a branch instruction, then whatever the output of that will go to Z in. Okay. At time 6, if it is a add instruction, then the result will go to Z in. Okay. So how to do that? So how that physically how that was done, in the sense, probably there may be a circuit something like this inside the ALU. So this circuit will take care of that. Okay. And that circuit, this circuit, whatever the functionality, it can be represented like this. So Z in is equal to what? T1. T1 plus, it is OR, right? So it is plus T6 into add. T6 into AND plus T4 into BR. Okay, because this is what? AND gate. Here we are using AND gate, so multiplication we are using. Okay, right? So this is how this is one example, like how a hardwired control is created, right? Similarly, here is another example for generating an end command. Okay, so here whenever there is a at T7, if there is an add instruction is there, then we will end. At time 7, if there is an add instruction is there, then we will go to end. Okay, similarly at time 5, if there is a branch instruction, uh, then we will go to end. What does that mean, you may ask? So again, it is taken from the previous examples. So in the first example, if you see, at time 7 we are ending. Okay, in the first instruction, at time 7 we are ending. Okay, but before that, just before that time 7, we performed an add operation. Okay, so that or add, the result of that add is available in Z out. Okay, Z out contains what? The result of the previous add. Okay, so at time 7, if there is an add operation, uh, at time 7, if there is an add operation, you end. So that's what the first thing means. Okay, and this and the last thing, what it says, in the sense, at time 5, if there is a branch. So if you see the next one, so here you see at time 5, this is execution of branch instruction. The Z out contains what? Z out contains the branch instruction. Okay, this fourth instruction is used to update the PC. Okay, this is used to update the PC with the address of the branch instruction. Okay, if you recollect, uh, originally PC will be 2000 before starting executing all these things. Okay, assuming that all these things corresponds to the instruction branch 2050, which we have discussed in the last class, branch 2050. Okay, after loading this instruction in the IR, what will happen to program counter? After loading this instruction in IR, originally this is program counter. After loading this instruction in IR, program counter will become 2004. 2004. Okay. Now how we will get the target address? To get the target address, what you have to do is you have to subtract uh, 2000, the target address, from the current value of PC. So if you subtract it, what you get is 46, and 46 should be added with the current PC. Okay, so you will get 2050. Okay, that is called as offset. Offset is 46. When you subtract the target address minus the current PC, that is called as offset. Okay, so this offset is added with whatever currently in PC. Okay, program counter, and that goes into what you call that that goes into Z. Okay, so Z contains what? The result of the branch instruction. Okay, so Z out contains the result, the target address of the branch instruction, then goes to Z out, and then it goes to PC. Okay, so basically this is the branch target address. Okay, after executing the branch you should end. After executing the branch you should end. Okay, so that here we are saying that here we are saying that what if T5 is a branch instruction, then you end. Okay, and you may ask what is this. So this is a unconditional branch. The first one is a unconditional branch. Okay, that is irrespective of, there is no condition. Always we say that go to that particular address 2050, execute that, and then after completing the branch you end. Okay, then there is something called as conditional branch. Conditional branch means only if there is a condition, we will only if the condition is met, the branch will occur, otherwise the branch will not occur. Okay, so let us assume that we want to convert this as a conditional branch. In that case, what I can do is, here I can add something called as n is equal to, if n is equal to 0. Okay, say if is here, if n is equal to 0, then end. Okay, if n is equal to 0, then end. So you may ask, what does that mean? So you may ask, like, what is that? What is that if n is equal to 0? Then end. Okay, so what is that n? So what is n in the sense? N represents negative flag. Okay, n represents negative flag. Okay, so previously we performed some addition, right? Previously we performed some addition. What addition? We added offset with the PC content we added. Okay, when you add the offset with PC, always you should get a positive value. Okay, in our case we are getting the value 2050, which is the target address. But assume that when you add, you got a negative value, minus 14 you got. So in that case, something wrong went off. Okay, so it means we are not calculating the target address correctly, because target address cannot be negative. Address cannot be negative. Address cannot be negative. So we are adding one more condition to further ensure that no other problem should occur. So we are checking whether if n is equal to 0. If n is equal to 0, then we say directly end, don't branch. Are you getting? So where we are adding this? At step 4 we are adding. So at step 4 there is one more command added. If n is equal to 0, that is n is what? Negative flag. Okay, n is what? N is what? Negative flag. Okay, so if negative flag is 0, then we say that end. Okay, if n is equal to, if n is not 0, then then it won't end, then this will execute, which is to do the branch. Are you getting? Okay, so if n is 0, okay, so just understand that if n is 0, it should end. If n is not 0, it should branch. Okay, that is the logic. So how do we hardware program that? How do you do that using hardware control? So that is what this logic is. That is what this logic is. So here you can see what it is doing in the sense T4. Okay, T4, right? This is at step 4. At step 4 only we are checking whether n is 0 or not. If n is 0, you should end. Okay, so if n is 0, then what would be not n? Here actually it is not n. If n is 0, then what would be not n? Not 0 is 1. Not of 0 is 1. Okay, then is it T4? Are you currently executing T4? let us assume we are currently executing T4. Yes, we are currently executing T4. Is n is not n is 0, so not of 0 is 1, so this is also 1. Okay, so in that case this line will be enabled. This line will be enabled and it will go to end. Okay, it will go to end. That is, the program will complete. Are you getting? That is, which instruction is, so program is completing, but before okay, of course it is completing, but before completing it, executing which instruction? T4 it is executing. After executing T4 it is completing. Okay, but see the case of what do you call, if n is 1, if n is 1, then this will become not of 1. Not of 1 is what? 0. Not of 1 is 0. Now also assume T4 is executing. If T4 is executing and if it is not, if it is 0, then this output will be 0. Okay, if this output is 0, then after T4 it won't end. After T4 it won't end. That is the point. Okay, right? Okay. Similarly, let us take the case for T5. At T5, okay, assume currently you are executing T5. Okay, say n is equal to 1. Say n is equal to 1. If n is equal to 1, then what will happen? This output will be 1. This output will be 1. So T5 is what instruction? T5 is actually branch instruction. T5 is to go to that branch and do that branch. So T5 executes. That is, the branch executes. After executing the branch, it will end. Okay. Suppose if n is 0, if n is 0, okay, then this T5 instruction will not execute because the output will be 0. Okay, so whatever the output, if this output is 0, then that instruction will execute and it will end. Okay, because finally what is happening here? Okay, right, after executing only it will end. Okay, are you getting? Say if T4 is 1, if T4 is 1, if n is 0, then this will be what? Negative of 0 is 1, so 1 and 1 is 1, so this is 1, so this will enable the OR gate. Okay, and the output is what? Output is 1, but it is enabled by which instruction? T4. So as a result T4 executes and T4 says what? End, just end. Okay, okay, but in the reverse case, if if T5 is 1, if n is also 1, okay, then in that case this becomes 1, right, and the output is 1, but output now it has become 1 due to which instruction? T5. What is T5? Branch instruction. So it will perform the branch and then it will end, right? So that logic is given like this. Okay, so there is no third input, so it is not an input. It just says that if branch is less than 0, if branch is less than 0, that is, if n is, if n is what you call, if n is equal to 0, then the branch won't execute. Okay, right, if n is greater than, if n is not equal to 0, then the branch will execute, right? That's the point. Okay, because you cannot have a negative value for the branch address. Okay, so if branch address is negative, if branch address is negative, then it will directly end. T4 will execute, which will make it to end. If n is positive, then T5 will execute, which will execute the branch and then it will end, right? Okay, and this can be written something like this: T7 into add, T5 into BR plus T5 into n, T4 into n dash plus branch on negative. Okay, B or n represents branch branch on negative. Okay, that is negative in the sense if n is 1 it will branch, if n is 0 it won't branch. Okay, so that's the point. Okay. So a complete processor can be visualized something like this. Here some more blocks were added. So there is a bus interface unit, because there will be a bus inside the processor also, which is called as internal bus, and the bus outside the processor, which is in the motherboard, which connects memory and other devices, are called as system bus. So there will be a bus interface unit which connects the internal bus with the system bus. Okay, and most of the modern processor has two cache. There is a separate cache for instructions and there is a separate cache for data. So the first cache is called as instruction cache and the next one is called as data cache. Okay, and this instruction unit is used to fetch instruction from the instruction cache. Okay, if the instruction is available in the cache, otherwise it has to fetch from the main memory, right? And then there may be multiple blocks of integer and floating point unit for perform arithmetic operation. Okay, it is not that the processor will have only one integer or a floating point unit. It can have more than one integer and floating point unit also, so that these arithmetic operations can be done simultaneously or in a parallel fashion, right? And these are the main memory which is connected to the external bus, and these are the IO devices. Okay, so this is a more detailed view of the processor organization. Okay, fine. So that's it about hardware control. um, so so let us stop here for this lecture. Thank you.